Yeah, then I skip to pass to the second part of the testing approaches. The second category is testing demotivation algorithms, especially dedicated for space environment. The first algorithm is single bit error, like we can receive the signal and the message, the checksum doesn't match, and usually it just dropping out. And what we could do, of course, we could check single bit error, yes, no. So our receiver didn't have it. The second path delay overlaps. It's known that due to this big path delay can be that different slots arrive with different delay. So that slots, even if they are not overlapping slots, they overlap at the satellite point of view. So it would be interesting to check, okay, if the beginning or a little bit of the end is overlapped and therefore cannot be decoded, could work something out? And of course, for the basic receiver, just 8 bits from the beginning can be cut, and then it doesn't work anymore. It needs this preamble. For the space receiver, it of course would be expected that even if you cut preamble out, you do have this, you can synchronize from the data your phase. The third test is about double Doppler shift, that we put 2 messages and try to find the nearest point to have them, because in space environment we have that for the overlaps, that even if we take 2 beams, one going right and one going left for our point of view, these have maximum like 6 kilohertz Doppler, and it is very nice to see actually how nearby 2 signals can get, so that we still can demodulate them. The fourth test is about overlapping fully 2 signals with different power amplitudes. You know, very popular this Demond-Remond approach, that you demodulate the strongest signal, subtract, and search for the next signal and iterate it until you don't find any signal anymore. That's the fourth test. And the fifth, multi-message overlapping case, when we overlap with quite similar powers and try to shift phases and time delays and see how it works. Like, for example, joint maximum likelihood estimation could show up its results. Since we tested a commercial receiver, we didn't have any results, of course, for the last 3 tests. There's no way. But for the space environment receiver, these would be expected to have some good results. Okay, and the third category of our test was the real-time environment test, and it's known from previous researchers from ESA. There is mainly 3 categories, which is of high importance: low density, middle density, and high density traffic. There, of course, will be different optimal points of operation to receive the best output of the demodulation. And I will shortly show some details on this real data simulator. It basically consists of 3 parts. One is chip generator, one is signal modulator, and the second is just to visualize. For the chip generator, it starts with real data input. So we take snapshot of some data, where the ship is, what's its name, where it is going to, its speed, and going direction. And then we propagate it forward, like we assume it is linearly moving. So with the same speed, of course, after 2 minutes, it could be that it's already driving in a coast inside, but we assume there is space. And then we do self-organized TDMR slot computation, so that every ship finds its own slot within 50-mile radius, 50 miles radius. Of course, we can vary that, and yeah, we calculate the messages to the output, check the orbit, modulate the orbit, and check from satellite all the delay paths, all the view angles, signal attenuation, delays, etc. And that's the output, how it looks like. Here's like which ship, here's which cell, here's time, cell, ship, and here's the message, and then there's satellite parameters, etc. So that all was written on one file, and further we do signal modulation. We take this file, convert to IQ, IQ data, and do signal propagation modeling. Currently it's quite basic one, but it includes all the 4 main blocks. So the distance attenuation, like turning down the signal power, signal timing shift, do a delay, then signal frequency shifts, we do the Doppler, we shift like 2.4 kilohertz or so, and antenna gain, like we modulate antenna so that it has certain beam width, and check what's the outcome. So, and finally we put it to software-defined radio signal generator. How we did that? We made with airplane overflow over Deutsche Bucht, and it was 3 hours with airplane, just scanning what's around there. And we took those data as the inputs. It's 1,218 ships. We modulated an orbit, and SAT is the name of the DOR satellite when it will be launched. And here I wanted to show you some results. Like we distinguish 2 cases. The best, like one case, it's a real situation with all the overlaps, and in red is it is in red, and in the blue is the best case. It means that if we detect the 2 signals are overlapping during the IQ modulation, we just take the strongest. So it's not real situation anymore, but we say, okay, it's the best one can perform if one have single slot demodulation. If per one slot one can output maximum 1 message, it's the best one can do. So that's the blue line. And here you see in the graph the provided number of messages. Then check on receiver how much receives it. If it is demodulated as it is, IQ without any signal processing. And then we include path attenuation. Due at distance, we include path delays, we include frequency shifts, and then we include finally the antenna gain. And it's quite, here you feel it being quite flat, but it also goes down. With each of environment inclusion, it just goes down and down and down. Yeah, on the right hand side you see in percentage the comparison. And just for this point, I also extracted how it looks in time. So it was overflow over Bremen, and it lasted for 700 seconds. And this is like receiving path with the antenna. We see that at the beginning it doesn't get out, then further it grows, and afterwards it diminishes again out. And just to note that assumptions were that chips are driving all at this speed, like we have 20 seconds supporting single channel. Of course, we have already modeled like different driving speeds, but just for the purpose that that the channel is full, we used this assumption, and our altitude was 720 kilometers, and simulation was done on plus 10 dB. Because actually, if we wouldn't do that, this would be like very, very low, and only when we switch antenna in, it goes up. If the antenna is, yeah, and then it would be quite dependent on how the traffic model is, because if for dense traffic model, if we would here switch antenna on, it would still stay low, and probably for very narrow band antenna, it will go up. Okay. So I will drive to the conclusions. So we showcase 3 testing approaches with 12 testing algorithms. And we conclude that it enables to derive physical wire characteristics. It enables to check if the receiver is ready for space environment. And it enables to model certain situations like overflows over real world data and to evaluate performance in that cases. On the right side you see the SAT picture, and it is planned to be launched in 2013 on the October. Yeah, if you have questions, I'd be ready to ask.
Thank you, Ines. Questions? Okay, I have a question. You just tested your receiver, not all other alternatives.
Yeah. And this is also not the receiver which is flying on the satellite, because those data I'm not allowed to show here. But this is commercial receiver.
Thank you very much. Yeah. Oh, excuse me.
Maybe I missed the point, but it seems the testbed. I'm not sure if your testbed complies with a multi-channel AIS receiver as presented in the previous presentation. So, do you intend to extend the testbed in the future to cope with multi-channel receiver, so antenna array and multi-channel receiver?
Yeah, I completely agree. Currently, it is single channel, and to extend it like that, it has more than one beams with different characteristics. It's very simple for the current setup. So I think I'm looking forward. It will be in a half year, definitely.